Hello viewers, welcome once again to this module on the estimation of parameters, the second part which we will discuss today. In the first part of the estimation, we had taken a look at a working method on how to develop the equations for estimation. In today's module, we will look at the estimation procedure in a more rigorous manner, that is with more technical rigor. So, let us begin as earlier with the example of the 3 variable regression. We know that the 3 variable model is written as yi equal to beta 1 plus beta 2 x 2 I plus beta 3 x 3 I plus u I. As mentioned earlier, we cannot estimate the random disturbance term, we estimate the rest of it, and the estimated equation is written as y hat I is equal to beta 1 hat plus beta 2 hat x 2 I plus beta 3 hat x 3 I, such that y I is equal to y hat I plus E I. So, y I is the actual equation or the observed equation, y hat I is the estimated equation, and the difference between the two is called the error of estimation. Please remember that this error of estimation is quite different from this random disturbance term. Here we are trying to estimate only the parameters and we are not at all trying to estimate the random disturbance term, and in estimating those parameters we find that there will be a difference between the observation and the estimation. That difference is called the error of estimation. The procedure that we use is called ordinary least squares. It is called ordinary least squares. It is called the OLS, ordinary least squares method of estimation. So, what exactly is this? Here we minimize the sum of square of errors with respect to beta 1, beta 2 and beta 3 hat. So, we choose beta 1 hat, beta 2 hat and beta 3 hat in such a way that the sum of squares of the errors of estimation is minimized. Let us go further into it. So, we have already seen that E I is equal to y I minus y hat I we know is beta 1 hat, beta 2 hat x 2 I and beta 3 hat x 3 I. So, the square of this is given by E I square, and the sum of these is called the error sum of squares. We get it by summing up from I going from 1 to n. So, this is the expression that we minimize with respect to beta 1 hat, beta 2 hat and beta 3 hat. Now, standard techniques of optimization apply. So, we write the first partial derivative of E I square should be equal to 0, I running from 1 to n, which implies if we take the first partial derivative with respect to beta 1 hat, we will get minus 2 summation yi minus beta 1 hat minus beta 2 hat x 2 I minus beta 3 hat x 3 I is equal to 0, which really means summation E I is equal to 0. That is very important. As already seen, the sum of all the errors is equal to 0. This term in the bracket is E I minus 2 times that equal to 0 means summation E I is equal to 0. So, summation of this term in the bracket summation E I is equal to 0. So, this is called the first normal equation that we denote as N1. Second partial is with respect to beta 2 hat, and we write del beta 2 hat of E I square equal to 0, which implies we have this x 2 I, and when we take the derivative with partial derivative with respect to beta 2 hat, we will get a 2 with a minus sign and x 2 I. So, this will be minus 2 as earlier, and we will have yi minus beta 1 hat minus beta 2 hat x 2 I minus beta 3 hat x 3 I as earlier, but multiplied by x 2 I, and that should be equal to 0, which is nothing but saying that if you take a look at the terms in the first bracket, this is E I multiplied by x 2 I, that is summation E I x 2 I is equal to 0. So, that is summation E I x 2 I is equal to 0, which is the second normal equation, and going in the same way we will have del beta 3 hat of summation E I square I running from 1 to n will be equal to 0, which will imply instead of x 2 now we will have x 3. So, I am writing it in one line, that is summation E I x 3 I is equal to 0, or you can also write it in expanded form yi minus beta 1 hat minus beta 2 hat x 2 I minus beta 3 hat x 3 I all multiplied by x 3 I, and then sum, and then write I running from 1 to n, that is equal to 0. So, that is your third normal equation. Now, there is an easy way to go about this in the further steps. We have 3 equations, we have 3 unknowns. So, we can solve for beta 1, beta 2, beta 3 all hats, beta 1 hat, beta 2 hat and beta 3 hat. We also have an easier way of making this derivation and getting beta 2 hat and beta 3 hat. What is it? Since summation E I is equal to 0, therefore, we can write E I is equal to y I minus y hat I, and since summation E I is equal to 0, therefore, summation y I minus summation y hat I is equal to 0. Therefore, we have one very important condition, that is y bar is equal to y hat bar. If we divide this by n and this by n, also the left hand side by n, that means E bar is equal to y bar minus y hat bar, and that is equal to 0. E bar is equal to y bar minus y hat bar, which is equal to 0, which means y bar is equal to y hat bar. Further, we introduce some notations. We say small y I is equal to capital Y I minus y bar, small x 2 I is equal to capital X2I minus X2 bar, and small x3I is equal to capital X3I minus X3 bar. So, these are called variables in deviation form. We make a mean correction. So, small y is in deviation form, small x2I is in deviation form, and small x3I is also in deviation form. Let us now use this information in the three normal equations, or more specifically we use this information in N2 and N3. So, from N2 we get summation EI capital X2I, summation EI capital X2I is small x2I plus x2 bar is equal to 0. Please see, small x is capital X minus x bar, small x2 capital X2 minus x2 bar. So, capital X is small x plus x2. So, small x plus x2 bar, and that means summation EI x2I plus x2 bar summation EI is equal to 0. But viewers, we already know that this part is equal to 0. Therefore, second normal equation in deviation form becomes summation EI x2I, I running from 1 to n is equal to 0. Similarly, if we look at the third normal equation, which is summation EI x3I capital equal to 0, then we can write it as summation EI small x3I plus x3 bar is equal to 0, which gives us summation EI small x3I plus x3 bar summation EI is equal to 0, where the second term is already equal to 0 by the first normal equation. So, the first normal equation already puts summation EI equal to 0, and we are left with EI x3I summation equal to 0. So, if we now collect the second normal equation and third normal equation, and if we write them down, then we obtain, as we saw, EI is equal to yi minus y hat I, but EI can now be written as yi minus y bar minus y hat I minus y hat bar, because y bar and y hat bar are the same. So, from the first term and from the second term we are subtracting y bar, which is equal to y hat bar, and we get EI is equal to small yi minus small y hat I. So, now this small y hat I means that the intercept term will go away. If you take away the mean, then this intercept term will go away. Capital X2 and capital X3 will be replaced by small x2 and small x3. So, this will be yi minus beta 2 hat small x2I minus beta 3 hat small x3I. So, taking all this information into account, we now write the normal equations in deviation form. This is also in the standard literature known as the model in deviation form. It helps us to make the derivations in an easier way. So, we write EI is equal to this yi minus beta 2 hat x2I minus beta 3 hat x3I. So, we write that yi minus beta 2 hat x2I minus beta 3 hat x3I, the whole thing multiplied by, as we saw in deviation form, it is EI x2I small, that means into x2I is equal to 0, and we have again EI, that is yi minus beta 2 hat x2I minus beta 3 hat x3I all into x3I is equal to 0. So, these are the final two equations from which we can obtain beta 2 hat and beta 3 hat. We will use simple simultaneous equation method to solve for beta 2 and beta 3 hat, or we can use for a larger k variable model, we can use the matrix form and we can solve for beta 2 hat and beta 3 hat. Once we obtain beta 2 hat and beta 3 hat, we know that y bar is equal to beta 1 hat plus beta 2 hat x2 bar capital plus beta 3 hat x3 bar capital, because this is equal to y hat bar, and y bar and y hat bar are the same because summation EI is equal to 0. So, once we obtain beta 2 hat and beta 3 hat, we can plug those values here and we can obtain beta 1 hat as y1 bar minus the other two expressions. Now, how do we come to these expressions? Let us see using algebra. So, the first normal equation, second normal equation and third normal equation converted into deviation form gave us EI x2I equal to 0 and summation EI x3I is equal to 0. And we had written these as yi minus beta 2 hat x2I minus beta 3 hat x3I times x2I is equal to 0 and yi minus beta 2 hat x2I minus beta 3 hat x3I times x3I equal to 0, which means yx2 is equal to beta 2 hat x2 square plus beta 3 hat x2 x3. Viewers, please take a look. Yx2 is equal to beta x2 square plus beta 3 hat x2 x3, beta 2 hat, beta 3 hat. And similarly, yx3 would be equal to beta 2 hat and x2 x3 plus beta 3 hat x3 square. Pair of simultaneous equations, we can eliminate either beta 2 or beta 3 hat and we can obtain the rest. For example, if you want beta 2 hat, you multiply this equation. We want to eliminate beta 3 hat, so you multiply the first equation by summation x3 square and multiply the second equation by summation x2 x3. So, beta 3 hat terms will get cancelled. Here you have yx2 summation x3 square, that is your yx2 summation x3 square, and the other term is x2 square x3 square minus x2 x3 whole square. So, x2 square x3 square minus summation x2 x3 whole square. So, we can eliminate and we can come to these results. How exactly does this carry over to the k variable model? We have already seen that for the k variable model, we have EI x j I is equal to 0, I running from 1 to n, and this j now runs from 1 to up to k. Simple logic. every time we are multiplying EI by the explanatory variables, the regressors. Now, how many regressors are there? There are k. Actually, in the deviation form, it will run from 2 to k. So, we have in deviation form k minus 1 normal equations. So, this is basically the idea. The product of EI and the jth explanatory variable in deviation form, the sum of those products must be equal to 0. And from here we can further develop the matrix algebra that will show us the final result of the beta hat vector, which is the entire set of betas in the k variable model. So, we have already seen that the k variable model can be written in matrix form. As we saw, the normal equations can be in terms of the original variables or the variables in deviation form. Accordingly, we have summation EI x j I running from I running from 1 to n, that summation must be equal to 0. And if you have original variables, then it is j running from 1 to k, like we had EI x 2i, EI x 3i, EI x 1i, which is 1 1 1. Or you can have in deviation form, which is EI x j I, again I running from 1 to n, but j this time is from 2 to k, because the first normal equation is already subsumed. So, therefore, we can just extend this to the k variable case. J will now go from 2 and not stop at 3, it will go up to k. And once again, what is the X matrix? This capital X. What is the small x matrix? Is this matrix in deviation form. So, writing this equation k times, j running from 1 to k means writing this equation k times for j equal to 1, j equal to 2 up to j equal to k. Instead of that, in matrix form we can simply write x prime E equal to 0, the transpose of this. That means the first column becomes the first row. So, this is, if you multiply this with the corresponding EIs, it becomes summation EI x 1 I equal to 0. If you multiply this transposing and making it a row, if you multiply this transpose times E, it becomes summation EI x 2 I is equal to 0, and on to EI x k I equal to 0. So, in matrix form we write it as x prime E equal to 0. Please note, not x e but x prime E. Similarly, in deviation form we will have EI x 2 I summation 0. So, what is x 2 I? This column. So, you transpose and make it x 2 horizontally and then multiply with EI. So, that will give you x prime E equal to 0, because that gives you x 2 the first row, this first column becomes the first row, the second column becomes the second row, and the kth column becomes the kth row. So, you have k times this expression, that is summation EI x j I is equal to 0. So, having written it in matrix form, you just substitute E is equal to y minus x beta hat, because y is equal to x beta plus u and y is y hat, actual or observed is estimated plus error. What is the estimate? X matrix times beta hat. So, that is the estimate. So, what is the error of estimate? Y minus y hat, that is y minus x beta hat. And if you now multiply, you will get x prime y is equal to x prime x beta hat, which means x prime x beta hat is equal to x prime y, which implies that beta hat will be equal to x prime x inverse x prime y. Similarly, if we are dealing with the model in deviation form, then we write small x prime y is equal to x prime x b hat, because y is the observed and small x b hat is the estimated. Remember please that b hat is only from beta 2 to beta k. So, beta is intercept plus all the slopes, and intercept is b1, beta 1, all the slopes together are represented as b. So, that b is beta through up to beta k. So, from here we have b hat is equal to x prime x inverse x prime y, and this expression when we did for the 3 variable model is exactly the 2 normal equations that we solved for beta 2 hat and beta 3 hat. So, in this module we have taken a look at the detailed technical derivation of the betas, the intercept and also the slopes, and we have done the model in terms of the original variables and also in terms of the variables in deviation form. The deviation form variables are useful because they compress the model and you can get estimates of the slopes only. So, in the next module we will take it further up from there and discuss how to use these estimates and what are the further characteristics of these estimates.